Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture 29 of this course, and where are we placed in this course at this stage? So far, we were in the past few lectures, we were looking at how molecules are detected in space, right? And we saw that we could detect molecules in space by obtaining light emitted by a star from a distant galaxy and comparing, the spectral signals of the light obtained from the star with the spectral signals of some molecules present on Earth. Based on this comparison, we know what the star is composed of. What are the molecules present in this star? All right. This is how we detect molecules in space. This is what we saw so far. Now, what is the key to the whole business? The key idea to the whole business is this concept of how light interacts with matter, right? So, light from a distant star, we get information by measuring the spectrum of light obtained from a very distant star. We get information about the matter that is present in outer space, correct? So this whole idea, the whole idea of interaction of light with matter is exceedingly important to our understanding of how molecules are detected in space. All right. So in the next few lectures, what we shall be doing is we shall be studying the interaction of light with matter in greater detail, in partially qualitative and partly quantitative detail. All right. Now, if we have to understand, the interaction of light with matter, we must first know what light is and what matter is, correct? I mean, interaction we know. Interaction is, some sort of an association, how they behave in the presence of one another, etc. So the phrase interaction we kind of know. But we still have to understand what light is and what matter is, correct? That's when we can get a full understanding of what happens when light interacts with matter. Is that fine? On that note, we shall today, study some interesting properties of light. Okay, we shall begin with light. And then we shall move on to matter. And after, let's say, approximately a couple-ish of lectures, we shall be in a position to understand the interaction of light with matter itself. Okay, yeah. So, light. What is light? Well, the funny answer to this is the opposite of heavy, but that's not what we are discussing here. Okay, right? We don't care about light, heavy, and all that. Light as in the light that is shining on us. The light that is shining on you and all that. What is light? Well, this question, has been enamoring people for millennia. Okay, let's not worry about all the pre-16th century discussion. Okay, so around the times, okay, right? At around circa approximately, Newton's time. Okay, we're talking about 1600s, right? So around 1600s, light was said to be made of particles. Okay, now what's a particle? We'll come back to that in a bit, okay, right? So around 1600, light was said to be made of tiny particles called as, I'm sure from high school you should recall the specific name given to these particles. They're called as what? Corpuscles, correct? Yeah. So light was said to be, some tiny particles just coming out from somewhere, right? Yeah. Now, in about, approximately 1700s, and till 1900, okay, or by 1900. All right, yeah, I'll put it this way, by about, all right. It was well established that light is actually not a particle, but light is what? Again, the other phrase you always consider when you compare a particle, it is with a wave, right? Yeah. So, you get me, right? So this is based on the idea that, light can reflect, light can refract, and all those phenomena. But properties such as interference, constructive interference, destructive interference, etc., had by close to 1900s given people an idea that light is actually a wave. All right. So look at this. So This was the proposal in around by around say 1600s and 1700, and subsequently by around 1900, light is said to be a wave. Now, see, we are introducing two new jargon in this class. What is it? We are introducing the two jargons, particles and a wave. Do we actually understand what particle and what a wave is? Everyone talks about it, right? Everyone talks about it right from approximately in our education system. We talk about particles and waves probably starting from your 11th standard, right? Where you encounter modern physics and the aspects of atomic structure for the first ever time. We say that light is both a particle and a wave, electron is both a particle and a wave, there is wave particle duality, etc., etc. But what actually is this particle? What is by the use of the phrase particle, what do I mean? And by the use of the phrase wave, what do I mean? Oftentimes, I find it surprising that several undergraduates, right, do not have a clear-cut distinction between particles and waves. We shall, look into that fundamental aspect right now. So, I'll tell you what particles mean. So, and what are the features of particles? Okay, what exactly do I mean by particle? And what are the features, of these particles? Now, would you consider yourself to be a particle? Yes, intuitively, right? Yeah, I'm a particle. You can say, okay, if you don't want to take into account living beings, let's consider the non-living entities. Well, this duster is a particle, this chalk piece is a particle, this piece of paper right in front of me is a particle, etc., etc., correct? So, this chalkboard is a particle, right? So, we kind of have an intuitive feel for what particle means. But, do you know the properties of particles? Well, different particles have different properties, but what's a common theme common to all the particles? Well, the first thing, okay, right? The very first property of a particle is that a particle occupies a well-defined position in space. In other words, the center of mass of this particle is ascribed to a unique set of coordinates. Center of mass is ascribed to a unique set of, we'll just use Cartesian coordinates, x, y, and z coordinates. Now, what do I mean by this statement? What I mean by this statement is that, hey, if for example, you take this chalk piece. Now, this chalk piece occupies a finite volume, a well-defined volume in space, correct? When I say, this chalk piece is here, let's say, in a small volume element corresponding to, a cylindrical volume element corresponding to roughly, say 2 centimeter cube in space, right? It is here. It is not over there or here. And because it occupies a well-defined volume in space, right? Its center of mass is unique to a particular, like XYZ coordinate. All right. So that's the fundamental idea about a particle. This is one aspect. Let's look at some more. The next point about a particle is that the number of particles, okay, this is the number conservation property. The number of particles, right, in any given space, right, volume, in any given volume of space, okay, right, in any given volume of space, it's better phrased that way. Is unique, all right, is unique and is well defined by a single number. By a single number, yeah. I'll tell you what this phrase means. So let's say, that like I take with me, some 2 big chalk pieces, right? Now, let's say that the whole span of this volume is close to approximately 12 centimeter cube space, okay, right? 12 centimeter cube space approximately, okay, right? Now, I know that there are 2 chalk pieces here. If I break it down further, right, particles can be broken, but if I break it down, I know that there are 4 chalk pieces, right? I've broken it into 2 pieces each. And if I further break it down, right, as many pieces I break down them into, there are that many pieces. All right. This point may sound obvious to you right now. You may think, what's the big deal? Why am I making a big fuss of it? But hold on, I'll explain the beauty very soon. Okay, right? So the key is that the number of particles in any volume of space is unique. It's unique because, if I say there are 2 chalk pieces, there are of course 2 chalk pieces, and it is well defined by a single number. Okay. In other words, I can always define the number of particles uniquely within a given volume. That's the second property of a particle. All right. The third property, okay. So the next property of particle is that, let's say that, any given particle is occupying a certain volume in space. Okay. When, a particle occupies some volume in space, right? Let's say I've already given to you the condition that, some particle is occupying certain volume in space. Okay, right? No other particle can occupy the same space, right? Given that one particle is occupying some volume in space, right? No other particle can occupy the same space, right? Displacing the original particle. This is of course subject to no other external force. Okay, right? When there is no other external force, then of course, if there is some external force, then you can displace objects, etc., etc. What I'm saying is, in a sense, if there is one particle present, in let's say some unit volume here, right? Only this particle is present. No other particle is present. If I can, of course, give some external force. In the presence of some external force, I could displace it and then get some other thing. But when something is already there and when it is not subject to any other external force, correct? This particle is always going to be existing. Are we clear? So far we've looked into 3 properties of particles. One is that a particle occupies a well-defined position in space. Point number 1. Okay. In other words, a particle is what is called as localized. All right. What do I mean by localized? Its center of mass can be uniquely ascribed to a particular set of coordinates. Point number 1. All right. Point number 2. The number of particles in any given volume is unique, right? If I say, there are 2 chalk pieces lying within some unit volume, there are only 2 chalk pieces. There are no more or no less. This is the second property. The third property is that, given that one particle occupies some volume in space, right? And that there are no external forces acting on it, the particle will remain intact. You cannot have any other particle in the same space. This may also sound obvious when I say that, like this chalk piece is here, right? Why should yet another chalk piece occupy the same volume? If I'm saying I'm here in the recording studio delivering a lecture, where else can I be? And in my space, who else can it be, right? If I'm already here, unless I'm pushed out or something, right? Do you get me? So this is this aspect. Now all these 3 points might sound obvious, but when we discuss them in the context of waves and compare them with waves, right? That's when the profoundness, the profoundness of the whole topic will come out beautifully. All right. So this said, let's look at the last property of a particle. The last and important property of a particle is that when a particle moves, okay, right, from point A to point B, both mass and energy are transferred from point A to point B. I'll just put it this way, okay, right? So notice this distinction. Let's say, that a particle moves from point A to point B, right? In other words, when I'm moving from here to, let's say, a few centimeters away here, on that side, right? You know that my mass is changing, correct? My mass is, my center of mass is changing its coordinates. I am, of course, moving, okay, right? I am moving. So you can understand that mass is getting transferred. It is not just mass. The kinetic energy, my kinetic energy is also changing, right? As I move from one point to another, right? My energy is also changing. I have not gone into the details of what type of energy is changing, by how much, etc. But know it broadly that when we consider the motion of a particle, both its mass and energy are transferred from one point to another point. Are we good? So these are, the key points about what a particle is. All right. Now, all of these points, some of these points might sound obvious. Of course, right? One particle is one particle. If this particle is here, where else can it be, right? Yeah. But in the context of waves, as I said earlier, right, all of these points will undergo a profound, will have a profound impact on you folks. All right. Okay. So now we'll look at the properties of a wave. The very first property of a wave, okay. The very first property of a wave is that a wave is highly delocalized. In other words, where do you encounter waves in the first place? We talk about waves, water waves, right? You talk about sound waves, you talk about light waves, etc. Do you ever talk about a wave that is static? In other words, a wave that could be ascribed to only one specific XYZ Cartesian coordinate? No, right? So a wave is highly delocalized. Okay. Now, what do we mean by a wave? A wave is nothing but some disturbance, okay? Some disturbance which has certain properties. The properties I'll be describing now to you, okay, right? So every time, like a wave is considered, you cannot uniquely, hinge a wave to any particular XYZ coordinate, okay? In other words, the wave's coordinates keep changing. All right, so this is the first point. So the wave is highly delocalized. We call this, when in comparison with a particle is actually highly localized. Okay, this is the first point. The next point is that, okay, now this is where it gets really interesting. You have all studied properties of waves, probably starting from your 7th or 8th standard in high school, correct? And you've seen that waves undergo what is called as constructive and destructive interferences. Are we clear? So waves do undergo constructive and destructive interference, right? So the point is, in any given volume, okay, right? In any given volume, you can never say how many waves are exactly there. You can never say how many waves there exactly are. This is a very important point. Now, recall that, in comparison with particles, right? In comparison, when we were discussing about the particles, we can precisely say, that in a given volume, the number of particles is unique and it is defined by a single number, correct? Whereas here, right, in any given volume, you can never say how many waves are exactly there. Are we good? Isn't it a fascinating idea? This is what makes waves amazing. Okay. The next point, okay, right? The next point is that, okay, right? Now, well, I'll just delete this phrase, particle and put wave. When a wave, occupies some volume in space, right? Many other waves, okay? Many other waves can occupy the same space. Isn't it amazing? Now do you understand the significance of the localization of a particle? And that, like, cannot have one particle atop another, right? The key beauty is that because waves undergo this phenomena called as interference, right? Constructive and destructive, you can neither define the number of waves, right? For example, even if you consider a standing wave, what have you been taught in school? Or in maybe, some initial phase of college? You have been taught in college that you can consider a standing wave, right? A standing wave is a wave, or a stationary wave as it's called, as a combination of moving waves which are going in opposite directions, two moving waves, right? So you can ask me, hey, a standing wave therefore comprises exactly of two moving waves. Well, the answer is, I'm afraid, it's not just two. It can be any even number traveling in opposite directions. It can be four waves. If you tell me a standing wave is made up of two waves, okay, right? I'll tell you, no, it's made up of four waves. Two waves traveling in this direction and two in another direction. All the parameters being the same, so everything cancel out. In other words, you can never, say how many waves there exactly are between any points A and B. That's an amazing point, okay? And in the wake of this point, right? In the wake of this point corresponding to waves, you understand the significance for the corresponding definition for particles. That is, the number of particles is fixed, whereas the number of waves is not. And you can never tell how many there are, right? The next point is, again, it's fascinating, right? When I tell you that, hey, some chalk piece is occupying a certain volume in space, it is this chalk piece, it is one particle. It is not no other chalk piece. But when we talk about waves, right? When we talk about waves, when we say that there is a wave, okay, right? There is a wave. The word wave occupies is not precise, but I hope you get the gist of what I'm trying to say. When there is a wave in some region of space, correct? You can have multiple waves atop the same wave. You never know how many there are because of the phenomena of interference, constructive and destructive interference. Are we good? In fact, even in the same course, right? I shall give you a brief introduction to what interference also and how interference is actually useful in detecting molecules in space. There is this whole technique called as interferometry, radio interferometry, via which you can detect molecules in space. We'll discuss that a bit later, okay? For now, please note that one property of a wave is that when a wave occupies some volume in space, unlike particles, for waves, many other waves can occupy the same space also. Okay. So, amazing, right? The distinction between wave and particle. And lastly, the last point is that, let's say, when a wave travels, okay, when a wave moves from point A to point B, right, only energy is transferred. I mean, I will explain what this means, okay? For example, I'll explain it to you in the simplest possible way. Let's say, for example, I throw this chalk piece at you, right? I throw this chalk piece. Now, what happens as I throw the chalk piece? Well, if the chalk piece is a particle, mass got transferred, some energy also got transferred. Now, I'm also speaking with you. Recall, as I'm speaking, what is getting transferred? My sound energy is getting converted, right, into whatever form of energy that you're assimilating it into, correct, right? And what is sound? Sound is a wave, correct? Sound is a wave, okay? So, as my sound waves travel to you, am I falling over you? I'm not, right? You get the point? So, as the sound waves travel, okay, right? As the sound waves travel through to you, from me to you, right? I'm the source, and you all are the observers, correct? Huh? As the sound waves travel, energy is definitely getting transferred. There is no question about that. But mass is not getting transferred, okay? Because as a wave travels, okay, it is the medium that moves. The wave, it is the particles in the medium, that actually move about. All right. But what happens is that the wave itself, right? There is no mass transfer due to the wave itself. All right. Are we clear? So when a wave moves from point A to point B, only energy is transferred, right, from the wave. Of course, the particles in the medium will move, okay. However, the wave itself does not transfer any mass. Are we good with this? So now, having understood, the key distinctions between wave and a particle, I'll summarize, what they are in one slide, okay. But now you see that back in light was assumed to be a particle until 1700, and then suddenly, it's a wave. So there's a dramatic change of perception of what light actually is, right? And so this fundamental understanding, right, is going to be of great significance in identifying molecules in space. Okay. So what I'll do next is I will just summarize. I will use this point, okay, and I will just summarize the key distinctions between a particle and a wave, so that you can see for yourself why these are two completely different entities. So a particle and a wave. So a particle is localized. Whereas the wave is delocalized. I just explained to you what this meant, okay? The next idea is that when we speak about a particle, right, the number is fixed. Number can be uniquely defined. In other words, in any given volume, if there are n number of particles, there are n numbers of particles. But the number of waves cannot be uniquely defined for the waves. All right, so this is a wave defined, DEFINED. Right. So the next point is that no two particles can be atop each other in a given volume of space. Okay. In other words, two particles can't occupy the same space. Right? Whereas for waves, we just saw that due to the phenomena of constructive and destructive interferences, two waves or more. Okay, so here also 2 is not a strict number. I'll put it or more. So what I've written is 2 or more. Okay, right? So 2 waves or more can occupy the same space. And what is the last distinction? The last distinction is that when moving, right? When moving, both mass and energy are transferred. When a particle is moving, both its mass and energy are transferred. But then when a wave moves, right, only energy is transferred. So, because the handwriting is a bit bad and then I've written it way down in the blackboard, what I'm saying is, when considering the motion of a particle, both the mass and energy are getting transferred, whereas in the case of a wave, only the energy is getting transferred. So these are the very important and subtle distinctions, not so subtle, but the obvious distinctions between waves and particles. Now they are like chalk and cheese, as they say, right? Proverbially, the waves are completely different from particles. Now, despite that, in the early parts of the 1700s and way until, like, let's say, until 1800s, light was thought to be a particle. And suddenly, like in the 1800s and definitely by about 1900, light was thought to be a wave. So we're talking about light being described as two completely different phenomena. All right. So in the next class, we shall see how to reconcile between these two phenomena and what actually light is. All right. Thank you so much.